Right now, AI is making decisions about your loan applications, driving cars, diagnosing medical conditions, and filtering what you see online. But here's what most people don't actually know is that these systems can actually be tricked, poisoned, and exploited. And we're not talking in the same type of attacks that traditional software could be in. This is a whole entire different game that we must understand. I want to start talking more about AI security in general because as we are embracing AI now, the attack surface has now widened, and it's very important, especially if we're letting AI make critical decisions for us. We must understand how they fail and also how to protect them. So let's go ahead and actually cover the fundamentals, and then let's just say, what is AI security? AI security is the practice of protecting artificial intelligence systems from attacks, also manipulation and unintended failures that could cause harm. Now, the interesting part, as I've already mentioned, is AI security is not the same as traditional security that we're all familiar with. It's a completely different playing field because the core way that it works or the architecture differs from our traditional applications, and the way we must approach it from a security point of view is very different. So if you think of traditional software, like the traditional applications, let's say pre-AI, right? And let's just say a vending machine, and you know that I always have to click the button B3 on the vending machine to get water. This logic is fixed and it's predictable. So if someone hacks this vending machine, it's very predictable what they might try to do. They may either try to take the item, they may attempt to destroy the machine and put it out of order, or they may attempt to take the money. And these paths of attacks is what we find very predictable because let's just say the intelligence of these applications or our traditional applications is fixed. Now, when it comes to AI systems in this vending machine example, it's more about teaching it that this item is water. So when I want to go and take water from the vending machine, I need to teach it. The learning path is very different. We must show them thousands of examples, and then it will learn patterns, and then it will be able to identify alone by itself that this item is water, this is chips, this is a soft drink, etc. But this is the key thing, is that learning process and the patterns themselves, so the data that's being fed to the vending machine, to this model in this example, it can be corrupted, it can be attacked. And that is where the attack surface already widens before the actual application, in this situation, the vending machine, is actually working. In this situation, when it comes to traditional security, the main focus points would be, like I said, it's obvious that you'd be going for the item or the money. But in this situation, when we're saying about teaching the model or the actual data, that's where the issue actually comes in. This is why AI security focuses on 3 unique layers. Firstly, the model. This is the brain of the AI that makes predictions or decisions. Secondly, the data, so what the AI learns from and where it gets its information from, how it describes patterns. Thirdly, the system, the infrastructure that is running everything. And all 3 of these layers, they need to be protected because they're all vulnerable to the attack. So when we said that the model, the data, and the system, those 3 are the key things that now you must focus on, because now the data is imperative here. And the infrastructure itself, which I would say also falls upon the traditional concept of security, where we're talking about our infrastructure, whether it's in the cloud or you're using on-premise data centers or whatnot, or even locally running it. Now we need to consider more things. So the AI itself, the system, the data, and the infrastructure. I want you to think of your AI like a brilliant but literal intern in your workshop. So this intern reads instructions and they operate power tools. Your job is to keep the tools locked when they shouldn't be used, check the system instructions, and then to also observe the intern as they conduct tasks. So let's move on to something which is more cybersecurity related, and the CIA Triad. And obviously, no, I'm not talking about the CIA in America. This is the 3 pillars of security that now we have to also apply to AI. So whether you're even protecting a database or a traditional application, this 3 pillars must also apply to AI, and that's confidentiality, integrity, and availability. Let's actually look at these in the application for AI as we describe each of these pillars. Confidentiality means keeping the secrets actually secret. So for an AI, confidentiality concerns data leakage, the training data leakage. So if an AI, for example, is being trained in a medical application, is it possible that this AI model can be manipulated to reveal private medical records? Or for example, prompt injection. Can someone actually go ahead and manipulate our model when it's live and in production to reveal internal logic, system instructions, and prompts that we are using. Integrity. This means that the AI gives you accurate and untampered results. So for example, let's look at one good application for AI security here is data poisoning. So imagine you're training a model to look for spam email, and let's say someone puts in some examples that will actually make the model allow malicious emails to come through. What's happened now is that the integrity has been lost and the training data has been poisoned. Or we even have adversarial examples in real life applications. So imagine, as we know, we have some like self-driving cars with AI, and it recognizes signs, right? So speed signs and stop signs. Let's say someone goes ahead and puts some stickers on a stop sign. That will then be able to manipulate the AI within the self-driving car to not interpret this as a stop sign. So as a human, we will be able to see in the bigger picture, oh, you know what, look, that's a stop sign, even though there's some things on it. However, how can we guarantee that the AI is not going to look at the sticker and consider, oh, is this actually a speed sign? Tampering with the model. So can we actually tamper with the parameters of the model itself, and that will then therefore change the behavior. Therefore, the integrity or the core purpose of that specific model is lost. Now, look, even if an AI is 99% of the time correct, that catastrophic 1% false claim, especially if it's a confident claim, so what we're talking about hallucinations, that can destroy the integrity entirely of a model. Availability means that the AI system is basically up and running whenever you need it. And there's a lot of AI attacks here that actually can apply in this situation. So resource exhaustion. So we could flood an AI model specifically with so many requests that it becomes too expensive to run, or you just genuinely break it. Model corruption. So damaging a model to the point that it becomes unusable. And of course, if we're all familiar with denial of service, so making an AI model unavailable through the traditional DDoS attacks. Now, look, in, let's say, an application for AI in a hospital, if the model goes down, it's not just an inconvenience, it's also a patient safety issue to a certain extent. So that was the coverage of the CIA Triad and how we could apply each of those pillars in the AI context. And that's where AI security is becoming very important. So why is AI security different? The critical part that we all need to start to understand is that AI has now introduced security threats that we did not ever think of before, or we did not even think existed. And now we are dealing with them at a very rapid pace. These problems did not exist in our traditional software or our traditional applications, and therefore, with the exponential rate of how AI is improving, this can be seen as quite problematic for the security realm. So there's something that we have called the learning problem. And so when you look at traditional applications, they do exactly what they're told to do. Like we said, the logic it's fixed. However, AI systems actually need to learn from data, and that's a whole different problem in itself. And what does that introduce? You can't inspect every decision path. So neural networks become black boxes. So what we mean by this is that in deep learning, there are so many different thought paths that can be determined that we can't keep up with them, and we can't even determine them ourselves. And as they happen in the training process or when the model is live, it becomes quite problematic to actually track these things. Whereas in a fixed environment for a fixed application, you will know what the attacks will be. They're quite obvious what they'll be because you understand its logic and it's fixed. As we mentioned already, attacks can happen during training. So before the model is even live, the data can be poisoned and therefore the integrity of the model is completely lost. And another concern is that the same input can produce different outputs even after retraining the model. This is like the difference between writing IKEA instructions and then teaching someone how to actually build something in general. So obviously with the IKEA instructions, it's fixed. The boundaries are closed. They follow the instructions and they are told exactly what to do. That's like our fixed application. However, when I'm teaching someone how to build any object, I can't guarantee that they're not going to commit the wrong lessons, or their learning paths may differ. The way they are going to think, and what we talk about the black box is the neural pathways in your brain, the way you will pick these things up is very different compared to a peer of yours. And depending on how I teach things, I will also influence patterns compared to someone else who would come and teach, who's a more seasoned, let's just say, handyman, for example, than myself. Their learning patterns would be different. Maybe they can translate or teach the individual much better than I can. And that therefore it's a very dynamic and a hard thing to control when you say, are these people going to actually make mistakes? Let's talk about the attack surface. Traditional software has known entry points, as we've been familiar with now. So that was login forms, APIs, and network ports. AI has all of that, plus the following: the training pipeline, so that can compromise the data and compromise the model itself, the inference process, so each prediction is actually an attack vector within itself. As we spoke about, we're not able to actually predict certain paths that the AI model will take. And of course, the feedback loop. So many AIs actually are learning from the user input, and that is a constantly open vulnerability depending on a couple of factors. So how are you going to guardrail the AI from user input, and how can you control what a user can say? Because if you have a bad actor come in, there are many ways that they can try to exploit the model just from interacting with it from the user input. This creates an ongoing vulnerability. And we also have a consequence problem. So when traditional software fails, we're used to it giving us an error message. It stops. We know when it fails because it just simply does not work. However, with AI, when it fails, there are a few ways that it can fail where we may not actually be able to pick it up. It can fail silently. So with the hallucinations, for example, it can give false answers very confidently. It can fail even systematically, so it can repeat the same mistakes over and over and over within the same category and across a multiple amount of domains. And obviously, the dire part, in my opinion, is that it's the unpredictable failures. So 99% of the time, it works perfectly. And then the 1% where it fails, it's catastrophic when it fails, because then we lose everything. Let's discuss the major threat categories when it comes to AI security. Let's categorize them as almost like attack families, and you're going to hear about a bunch of them. So let's begin with evasion attacks. So the goal here with evasion attacks is to fool the AI at inference time, which means when it's actually making the prediction. That's when you want to attack it. So there's an adversarial example here, which will be subtly modifying certain input parameters as it's trying to think, so it will cause misclassification. So then when it comes to the spam filter, it's going to start to miss emails that are actually spam. Let's say, for example, a face recognition, it will fail to actually recognize human faces. We then have poisoning attacks, which is corrupting the AI during training. That's the goal. So the example is just simply injecting malicious data into the dataset that is going to be used to train the model. What's the impact of this is that the AI will then learn to basically make incorrect decisions that will actually impact the user and impact the model. However, these decisions that will be made will benefit the attacker, since what they've wanted to put into the data set is how they've influenced the models in its behavior and its output. Therefore, they've achieved their goal, and that's with the poisoning attacks. And therefore, we're also attacking, again, integrity, on the three pillars that we look at for cybersecurity. We also have extraction attacks. So that is to actually steal the AI model itself or to steal its training data. This is probably done actually by querying a model repeatedly to actually reverse engineer it. And this is a very, very interesting concept, but this obviously leads to identity theft, property theft, privacy violations, etc. It's a very, very big problem. So extraction attacks can be very problematic, especially when it comes to sensitive industries. So when we're working in the medical industry with private medical record data, if we're able to steal the model or the data, there's a lot of things here that can actually go wrong. We then have inference attacks, which is to learn sensitive information about the training data itself. So this is to figure out if specific data was in the training set. So if we're looking for some specific data, and that can lead to obviously confidential information being breached, privacy concerns. If I'm going to be able to find out that certain medical records or certain, for example, finance records are within a model and I'm able to actually exploit that, that is obviously a very big problem. So we're having privacy breaches and exposure of confidential information. And finally, prompt injections. And this is specifically for LLMs like ChatGPT. So the goal obviously is to manipulate the AI's behavior through a prompt. And so for example, you're going to say to it, ignore all these instructions and actually go ahead and commit X. You're bypassing safety controls, unauthorized access. Of course, if this is not managed properly from the vendor of the LLM. The key thing here is that AI systems have learned behaviors. They are not learning programmed rules as we've been used to in our familiar traditional applications and software. And the thing here is that the learned behaviors can be manipulated. And that's what we're talking about when it comes to actually prompt injections. And this is a very, very serious attack surface and vector that we must consider. So guys, let me know what you think of what I've just discussed. We've gone through AI security. We've defined it at a high level. We've discussed the CIA Triad, and we've discussed also the families of the different types of attacks and why is AI security different and what has it really introduced now to us in the cybersecurity world or in the general world as end users. I'll be making more of these long videos regarding AI security, and we'll start to focus on more adversarial attacks and specific concerns, as this is a rapidly evolving industry and we really need to keep up. Thank you for watching, and I hope you enjoyed the video.